Hey Bulldogs, we are continuing our study of optimization. This is an example of a problem that includes an exponential function. And there are just an infinite number of applications of optimization. So I just wanted you to see one other variation and in a different context that we've seen already. So the story goes, we have a new pain-killing injection, which is administered, and the effect is modeled by this function. And t is greater than or equal to 0 and represents the time in hours after the injection. At what time is the drug most effective? You know, what might be more applicable to you is maybe you're not feeling well, your mom or dad gave you Tylenol, and you want to know when that Tylenol is going to be most effective, something like that. All right, so we've got a function, e of t equals 750t e to the negative 1.5 t power. And I want to know when we have a maximum value. So I am going to find my derivative, set that equal to 0 to find my critical values, plot it on a number line, and test around the critical values to determine where I have a maximum. So to find the derivative of this function, we have a variable expression, 750t, times another variable expression. So that means I'm going to use my product rule. So my first expression carries down, times the derivative of the second. So the derivative of e to a power is e to that same power. And then I have a little chain rule. So the derivative of the inner function, negative 1.5t, would be negative 1.5. That's the first part of my product rule. Second part is plus the second expression, e to negative 1.5t, times the derivative of the first. So the derivative of 750t would be 750. And we're going to set this function equal to 0. And we're going to clean that up a little bit. Now, actually, since I'm going to wind up factoring this in order to solve it, I'm not going to multiply the 750 times the negative 1.5 because I'm seeing they both have a 750. So I'm just going to dive right into factoring this. And I know I can factor a 750 out. I also can factor out an e to the negative 1.5t. And what that leaves me with here, I'm going to have that t left over and negative 1.5. And on this side, I'm just going to have plus 1, since that completely factors out to the front. And we're going to set both of these expressions equal to 0. So I'm going to divide by 750. And at just glancing at this, e raised to a power, so 2.71828 raised to a power will never give you a 0. So you actually get no critical values from this first expression. But if you didn't realize that and you started solving, to solve an exponential function like this, I would take the ln of both sides. And at that point, ln of 0 does not exist. You can only take logs of positive numbers. So even at this point, you're going to get no critical numbers from that. And then we're going to set negative 1.5t plus 1 equal to 0. So we'd have 1 equals 1.5t. And if I divide by 1.5, I'm going to get 2/3. So when my time equals 2/3, that is when I'm going to see my greatest value. If you approximated that, that'd be 0.6 repeating. So that's when I'm seeing my injection have the greatest effect. And so this problem is in terms of, let's see, hours. So 2/3 of an hour. If you were thinking in terms of minutes, that would be equivalent to 40 minutes. So 40 minutes after you have that drug injection, we're seeing the greatest effect on the body. If you wanted to test this out, you can always sketch this. So I've already got it sketched in here, this to this side. So we're just going to look at a visual representation of this. So if I were to drop this function in for y1, remember we've got input with x instead of t, so 750x e to the negative 1.5x, and I'm going to graph this thing. And when you graph this, you're probably going to start with a function that you really can't see much of. I know right off the bat I've got some high values here. I can definitely see this graph goes up really high, and that's where I'm looking. That's what I'm looking for is my maximum in there. So if you're not sure how high to make it, hit your trace key and you can kind of cheat. Look at your Y values. See how high up they go. 144, 172. It looks like it goes up as high as 182. So I'm going to go to my window and I'm going to maximize my Y value out to, let's say, 200. And that should give us a better view of the maximum that we're looking for in our graph. There it is. We're trying to find this point right here. So let's double check. We think it's at 2/3 or 0.6 repeating. So I'm going to go to my calculate menu. So that is second calculate. And I'm going to choose the option of identifying a maximum. This is how you did this in pre-calculus, before you knew how to differentiate functions. And I'm going to make sure my cursor is up to the left, hence the left boundary request. Now it says right boundary, go to the right. Do you want the calculator to guess? I sure do. And we get 0.6 repeating. There it is. So that is the exact same solution that we got when we found that maximum by hand. Now, the one thing I did not do is I did not test this on a number line. So if I was testing 0.6 repeating, if I were naturally stopping at 0, we could plug any number to the left in, and you can include 0 in that. So if you raise e to the 0 power, you're going to get a positive 1 times 750, which is a positive, and then 0 plus 1 is a positive, so we get a positive for this first expression. And then when you substitute a number in over here, a large number, or you could just substitute in even the number 1, but you could do 1 million, for example. This expression would be negative 1.5 times a million, so that's going to be significantly larger, so this would be a negative expression. And then over here, e raised to a negative 1.5 times 1 million power is going to be a value. Remember, the negative exponent generates a fraction, so it's pushing that into the denominator and making a very large fraction. It's not going to make the expression negative. That's still going to be a positive expression, so that product would be negative. So that confirms, in fact, that we do have a maximum here. Okay, thank you so much for listening to kind of just a random other application, and in this case, it was one that included an exponential function. Good luck to you.